In the autumn of 1943, deep beneath the chalk cliffs of northern France, thousands of forced labourers began carving into the earth. They were building something unprecedented, something that would make the V-1 flying bombs and V-2 rockets look primitive by comparison. The Third Reich called it the Hochdruckpumpe, the high-pressure pump. Allied intelligence would later designate it Vergeltungswaffe 3, the V-3, a weapon so ambitious, so radical in its engineering, that it promised to change the very nature of modern warfare. This was not merely another gun. This was a technological concept that challenged the fundamental physics of ballistics. A cannon so massive that it had to be built directly into the French countryside. A weapon designed for one purpose only: to rain devastation upon London from over 160 kilometers away, continuously, relentlessly, without pause. Today, we examine why Nazi Germany invested enormous resources into this engineering marvel. We analyze the revolutionary multi-chamber principle that made it theoretically possible. And we investigate why, despite the genius of its design, the V-3 became one of the most spectacular failures of Hitler's vengeance weapon program. To understand the V-3, we must first understand the strategic situation that created it. By 1943, the war had turned decisively against Germany. The Luftwaffe had lost the Battle of Britain 3 years earlier. Allied bombers were now systematically destroying German cities and industrial centers. The Eastern Front was consuming divisions at an unsustainable rate. Adolf Hitler was obsessed with retaliation. He demanded weapons that could strike back at Britain. Not mere pinpricks, but sustained terror that would break civilian morale and force Winston Churchill to negotiate. The German word for this obsession was Vergeltung, vengeance. The V-1 flying bomb could reach London, but it was slow, flew predictably, and British defences were shooting them down in increasing numbers. Anti-aircraft guns, fighter aircraft, and even barrage balloons were neutralising this threat. The V-2 ballistic missile was unstoppable once launched, but it was hideously expensive to produce and could only carry a relatively small warhead. Neither weapon could deliver the volume of explosives that Hitler demanded. What the Führer wanted was simple in concept, but seemingly impossible in execution. He wanted hundreds of explosive shells landing on London every single day. Not dozens, hundreds. A continuous bombardment that would overwhelm civil defense, destroy infrastructure, and terrorize the population into submission. Conventional artillery could achieve such rates of fire. A single gun crew could launch multiple rounds per minute. But no artillery piece in existence could shoot 160 kilometers. The physics simply did not allow it. Or so everyone believed. Enter August Cönders, a brilliant engineer working at the Röchling steelworks in the Saar region of Germany. Cönders had been wrestling with a problem that artillery designers had faced since the Great War. How do you make a projectile travel faster and farther without making the gun barrel impossibly long, or the propellant charge so powerful that it destroys the weapon itself? The conventional approach to increasing range was straightforward. You pack more propellant behind the shell. The expanding gases accelerate the projectile down the barrel. More gas pressure means higher velocity. Higher velocity means greater range. But there are fundamental limits to this approach. The pressure becomes unmanageable. The barrel erodes after just a few shots. The gun becomes too heavy to transport. The gains diminish rapidly while the problems multiply. Cönders proposed something radical. A concept that turned conventional artillery design completely on its head. Instead of one massive propellant charge at the base of the barrel, what if you used multiple smaller charges positioned along the entire length of the barrel? Each charge would ignite in sequence as the projectile traveled past, adding velocity at precisely the moment when the previous charge's gases began losing pressure. Consider the concept this way. A sprinter does not reach maximum speed instantly. They accelerate gradually, building velocity over distance. Now imagine if, every 10 meters along the track, someone could give them an additional push at exactly the right moment. Not one explosive start, but continuous acceleration throughout the entire race. This was the multi-chamber principle, the Mehrfachladungsgeschütz. The gun barrel would have pairs of angled side chambers along its entire length. Each pair would contain a propellant charge. As the projectile passed each pair, the charges would ignite automatically, either triggered by the projectile itself or by the pressure wave traveling ahead of it. In theory, this meant continuous acceleration. A barrel of 150 meters could achieve muzzle velocities that seemed impossible. Velocities exceeding 1,500 meters per second, nearly 4 times the speed of sound. Enough to send a 140-kilogram explosive shell over 160 kilometers. From the cliffs of northern France directly to the heart of London. The German Army's Weapons Development Office was intrigued. In January 1943, they authorized initial testing of the concept. The results were promising enough to attract attention at the highest levels. By May of that year, Albert Speer himself, the Reich Minister of Armaments, had approved full-scale development. The project received the codename Hochdruckpumpe, high-pressure pump, a deliberately misleading name designed to confuse Allied intelligence. The plans that emerged from Röchling and the Army Weapons Office were staggering in their ambition. The primary installation would be built at Mimoyecques, a small farming village in the Pas-de-Calais region of France. Here, just 15 kilometers from the English Channel coast, German engineers would construct not one gun, but 25. 5 separate batteries of 5 guns each, all aimed at a single unchangeable target, London. Each gun would be capable of firing approximately 1 shell every 12 seconds once the system was perfected. 25 guns firing continuously meant roughly 120 shells per hour, nearly 3,000 shells per day. Day after day, week after week. The weight of explosives landing on London would exceed anything the V-1 or V-2 programs could deliver. But building such a weapon required solving engineering problems that pushed 1940s technology to its absolute limits. The challenges were immense. First, consider the barrel itself. Each gun required a barrel approximately 140 meters long. This was not a weapon that could be manufactured in a factory and transported to the front. It had to be assembled in place, section by section, with tolerances measured in fractions of a millimeter. Any misalignment would cause the projectile to jam or the barrel to rupture catastrophically. Second, the side chambers. Each barrel required approximately 28 pairs of lateral chambers, angled at precisely 45 degrees to the main bore. The propellant charges in these chambers had to ignite in perfect sequence, within milliseconds of each other. If a charge fired too early, the additional gas pressure would actually slow the projectile. If it fired too late, the projectile would have already passed, wasting the charge entirely. The timing mechanism had to be foolproof, operating reliably under extreme temperatures and pressures. Third, the projectile design. Conventional artillery shells were simply not designed for such extreme velocities. The aerodynamic heating from air friction at 1,500 meters per second would be intense. The acceleration forces during firing would be brutal. The shell needed to be strong enough to survive launch, but still carry a meaningful explosive payload over the entire distance. Fourth, and perhaps most challenging, was the infrastructure required. The guns could not simply be placed on the surface. They had to be protected from Allied air attack. At Mimoyecques, German engineers designed a fortress unlike anything built before. The guns would be installed inside inclined shafts drilled directly into a chalk hillside. Each shaft would angle upward at 50 degrees, aimed precisely at London. The barrel would be assembled inside the shaft, completely protected from aerial observation and attack. Only the muzzle would emerge from the hillside, hidden beneath camouflaged concrete bunkers. Above the gun shafts, the Germans planned to pour a protective dome of concrete 5.5 meters thick. This was designed to resist even the largest bombs in the Allied arsenal. Beneath this dome, the infrastructure would include ammunition storage, crew quarters, ventilation systems, power generation, and an underground railway to transport shells from supply depots to the firing chambers. Construction began in September 1943. Over 5,000 workers, mostly forced labourers from Eastern Europe, descended on the quiet French countryside. They worked in conditions of extreme secrecy, not knowing exactly what they were building, only that it was important to the war effort. The chalk bedrock proved both a blessing and a challenge. It was soft enough to excavate relatively quickly, but unstable enough to require constant reinforcement. Workers drilled and blasted through over 100,000 cubic meters of rock. Narrow-gauge railways carried the debris out of the tunnels, while concrete mixers poured thousands of tons of reinforced concrete to line the shafts and chambers. The conditions for these labourers were harsh beyond imagination. They worked 12-hour shifts in cramped, dusty tunnels with inadequate ventilation. Food was scarce. Medical care was minimal. The threat of Allied bombing was constant. Historical records suggest that many workers did not survive the construction process, falling victim to exhaustion, accidents, and the consequences of the increasingly intense bombing campaign. Because Allied intelligence had noticed Mimoyecques. British reconnaissance aircraft had photographed the construction site as early as November 1943. The images showed massive earthworks, concrete structures, and railway spurs leading to a hillside. Analysts were puzzled. The installation did not match any known weapon system. It was not a submarine pen. It was not a conventional artillery battery. It was not a V-1 or V-2 launch facility. What was it? The British established a special investigation team to study the photographs. They noted the inclined shafts disappearing into the hillside, all aimed in a northwesterly direction, toward England. The analysts made a critical connection. The angle of the shafts, approximately 50 degrees, matched the theoretical firing angle required to achieve maximum range from heavy artillery. Whatever was being built at Mimoyecques, it was designed to shoot at Britain. The British did not know the technical details of the multi-chamber concept. They did not know about August Cönders or the Hochdruckpumpe program, but they knew enough. This installation, whatever it was, had to be eliminated. Operation Crossbow was the Allied code name for attacks against German long-range weapon sites. Mimoyecques became one of its highest priority targets. Beginning in November 1943, Royal Air Force bombers began striking the site. The early raids were ineffective. The concrete bunkers being constructed were too strong for conventional bombs. The German anti-aircraft defences were formidable. Workers simply repaired the damage and construction continued. But the Allies had a new weapon in development, a bomb specifically designed to penetrate hardened targets before exploding. It was called Tallboy, designed by the brilliant British engineer Barnes Wallis, the same man who created the bouncing bombs used against the Ruhr dams. Tallboy was a masterpiece of weapon engineering. Weighing over 5,000 kilograms and measuring 6 meters in length, Tallboy was designed to penetrate deep into the earth before detonating. Dropped from high altitude, it would accelerate to supersonic speed, punch through concrete and rock, and create an underground earthquake that would collapse tunnels and foundations from below. On July 6, 1944, exactly 1 month after D-Day, a force of Lancaster bombers from the Royal Air Force's elite 617 Squadron attacked Mimoyecques with Tallboy bombs. The results were devastating. Multiple Tallboys struck the hillside, penetrating deep into the chalk before detonating. The underground explosions collapsed tunnel sections, ruptured the carefully aligned gun shafts, and buried construction equipment under tons of debris. One bomb struck directly above a gun shaft, destroying it completely. The Germans assessed the damage with growing despair. Repairs would require months of additional work. The precision alignment of the gun barrels, already an immense technical challenge, would have to begin again from scratch. And there was no guarantee that the Allies would not simply return with more Tallboys. They did return. On July 17th, another raid caused additional damage. On August 4th, yet another attack. By this point, the German command structure was in turmoil. The Allied armies had broken out of Normandy and were racing across France. The question was no longer whether Mimoyecques could be completed, but whether it could be completed before Allied ground forces overran it. Meanwhile, at the testing facility in Mizdroy on the Baltic coast, the technical problems with the V-3 were proving even more intractable than the construction challenges. The multi-chamber concept worked. That much was clear from testing. Projectiles did achieve higher velocities than conventional guns, but the practical problems were severe and growing worse with each test firing. The barrel wear was catastrophic. The sequential charges, each creating its own pressure wave and thermal shock, eroded the bore at an alarming rate. After just a few dozen rounds, accuracy degraded significantly. The barrel would require replacement, a process that would take the fixed installations at Mimoyecques days to complete. The side chambers presented their own difficulties. They frequently misfired, fired out of sequence, or failed to ignite at all. When charges fired at the wrong moment, the results could be explosive. Several test barrels ruptured during firing, demonstrating the narrow margins for error in the system. Most critically, the specially designed projectiles proved aerodynamically unstable. The shells, called Spring Granite 4700, were fin-stabilized rather than spin-stabilized like conventional artillery rounds. At extreme velocities, these fins experienced flutter and vibration that sent the shells tumbling off course. The dispersion pattern was measured not in meters, but in kilometers. A weapon that could not hit a target the size of London was militarily useless. The engineers worked frantically on solutions. New fin designs, new propellant formulations, new timing mechanisms for the side chambers. But each solution created new problems. Time was running out. In August 1944, the V-3 program received a mortal blow. Not from Allied bombs, but from the Allied armies themselves. General Patton's forces were racing across France at a pace that astonished even optimistic Allied planners. The liberation of Paris occurred on August 25th. By early September, Allied troops were approaching the Pas-de-Calais. On September 5th, 1944, Canadian soldiers of the 3rd Infantry Division reached Mimoyecques. They found an abandoned construction site. The German garrison had fled just days before, leaving behind the massive concrete structures, the partially completed gun shafts, and thousands of tons of construction equipment. The dream of bombarding London with the V-3 supergun was over. But this was not quite the end of the story. While the Mimoyecques installation was being abandoned, a smaller, simpler version of the multi-chamber gun was actually deployed in combat. At Lampeden, in the Moselle region, the Germans installed 2 shortened V-3 guns. These were not the massive 140-metre weapons designed for London. They were smaller, approximately 50 metres long, with correspondingly reduced range. Their target was not London, but the recently liberated city of Luxembourg, seat of General Omar Bradley's headquarters and an important communications hub. Between December 30th, 1944, and February 22, 1945, these 2 guns fired approximately 183 rounds at Luxembourg. The bombardment caused damage, some casualties, and considerable confusion. But it had no strategic impact whatsoever. The accuracy was poor. Many shells fell in open fields or forests. The explosive payload of each round was limited. And most importantly, by this point in the war, Germany was fighting for survival on multiple fronts. Two small guns firing at a secondary target meant nothing in the grand strategic picture. In February 1945, advancing American forces overran the Lampedusa position. The guns were destroyed by their crews before capture. So why did the V-3 fail? The lessons are instructive for understanding both the strengths and limitations of German wartime technology. The multi-chamber principle was theoretically sound. Physics validated the concept. August Cönders had identified a genuine solution to the range limitation of conventional artillery. With unlimited time and resources, the engineering problems might have been solved. But Germany did not have unlimited time or resources. The V-3 program competed for materials, skilled labor, and manufacturing capacity with a dozen other weapon systems, many of which were more immediately useful to the war effort. The steel and concrete poured into Mimoyecques could have built conventional fortifications on the Atlantic Wall. The engineers struggling with side chamber timing could have improved the V-2's reliability. The fixed nature of the installation was a fatal weakness. Unlike mobile artillery or rockets, the V-3 could not be concealed, moved, or retargeted. It was a sitting target for Allied bombers, who could attack it repeatedly until it was destroyed. The Barnes-Wallis Tallboy bombs proved that no amount of concrete could protect a fixed installation against determined precision bombing. The technical challenges were underestimated. The Germans had a pattern throughout the war of rushing revolutionary weapons into production before the engineering was mature. The Me-262 jet fighter, the Type 21 submarine, the V-2 rocket, all suffered from reliability problems stemming from premature deployment. The V-3 would likely have followed this pattern had it ever become operational. And perhaps most importantly, the V-3 reflected a fundamental misunderstanding of how modern wars are won. Even if every shell had landed on London, even if thousands of British civilians had perished, it would not have changed the outcome of the war. By 1944, the industrial might of the United States and the Soviet Union had made German defeat inevitable. No vengeance weapon could alter that arithmetic. The ruins of Mimoyecques still exist today. After the war, the French government partially demolished the site, collapsing the underground galleries and filling many of the shafts. But portions remain accessible, converted into a museum dedicated to the V-weapon program. Visitors can walk through the surviving tunnels, see the remnants of the massive construction effort, and contemplate what might have been. The V-3 stands as a testament to both German engineering ambition and the hubris of believing that wonder weapons could substitute for sound strategy. It was a technological marvel that existed at the very edge of what 1940s engineering could achieve. It was also a colossal waste of resources that contributed nothing to Germany's defense and everything to the suffering of the workers who built it. In the end, the high-pressure pump pumped nothing but German blood and treasure into the chalk cliffs of France. The guns that were supposed to devastate London never fired a single shot at their intended target. The vengeance that Hitler craved never materialized, and the war continued on its inevitable course toward German defeat. This is the story of the V-3, a weapon that promised everything and delivered nothing, a monument to the dangers of placing faith in technology over strategy, and a reminder that in war, the most impressive engineering is worthless without the resources, time, and circumstances to make it work.